And we introduced it as something that could be derived from the gamma function, but this is, in most treatments, this is the primary definition of the beta function. And it is an integral equation, so it kind of has the same, is defined through the same principle as the gamma function. I have some dummy variable t that I'm going to integrate up, and it's got some unknown parameters. In this case, I'm calling them x and y. But in this case, I'm just integrating from 0 to 1. And we're not really into complex stuff yet. That'll be how we end the quarter. But what needs to be true is if these are complex numbers, the real part of both x and y needs to be positive. So in the same way that the gamma function blew up along the negative real line, and for certain values, it has what are called poles, the beta function also will blow up. And you can imagine why this is the case, because if I have negative values of x, well, I have like 1 over t, and 1 over t will blow up at 0. So this isn't really that exotic of a condition. So this is the thing. It's really important. So it shows up in a lot of statistics problems. It shows up in a lot of StatMech, therefore, and it actually even shows up in some classical mechanics problems. So we'll finish talking about the beta function by solving a problem that you had to kind of cheat to solve in 1230. So there's nothing that you shouldn't be able to understand about how I got from the first line with the t's to this. It's all some pretty vanilla transformations of variables and the normal trick that we used before, but it's not worth going over on whiteboard. So that's the separate video that's been posted already. There's a trigonometric form of this. So it's actually a couple of changes of variables will get you from here to here. And along the way, or in the next expression, you can see something pretty obvious about the symmetry of the beta function. So it doesn't matter if you flip the arguments. So it turns out this is also true. And somewhere you might see this actually as the definition of the beta function, something to do with gammas. And if they're integers, you can say this, but I'm going to be less excited about this definition because, at this point we've transcended factorials and we've extended them to the real line. So we'll just kind of say like node. Right. But through this, you can see the applications to statistics. So this kind of looks like maybe I'm, choosing red and blue balls out of a bag, maybe with or without replacement or something like that. And then so finally we have this note. There is a symmetry on the arguments. So bxy equals byx. Is there a question?
Yeah, shouldn't it be -2 on the bottom of the x plus y minus?
So yeah, good question. So if you look at what's happening, so I'll take gamma of x plus y, and I could write it all out from 0 to infinity, e to the minus, da 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 da. Or I could just think about changing variables and just defining x plus y to be like m or something like that. So this is gamma m, so it would be m minus 1.
I see. Okay.
So it's the whole thing, x plus y. Yeah. Yeah, so I think you're thinking about whether or not you can factor gamma x plus y into gamma x plus gamma y or something like that, or their product, which turns out you can't. So it's a little bit too grubby to do that. Okay, so that's the thing. Let's just try to use it. And my claim is that you can do this without any help. Okay, so eventually, if you do a lot of these, you should be able to calculate this in your head, but pencil, paper, fine. Just see if you can do it without Mathematica, just knowing what you know about the definition of the beta function written up there and what you know about the gamma functions. I see what seems to be looks of acknowledgement that one way or another you're done with this problem. Anybody happy with their answer? Any form is fine, either numerical or decimal, or if you need to in terms of gamma functions or factorials.
I got 1 over 360.
Yes, it is 1 over 360, which would be like 0.002 or something like that. And you did this by just identifying the exponents and saying like, hey, it's a beta function, turned it into gamma functions. Yeah, perfect. So this is how this works. And it's not as easy as it seems or sounds sometimes. So we'll go through an example of a difficult hidden beta function in an old classic physics problem. But this, okay, the extent of my trickery is that I gave you x's and, the form of the dummy variable which gets integrated out, doesn't matter anyway, was t's. So all I really have to do is identify these exponents, right? So what is y minus 1 and what is x minus 1? X minus 1 is 2 and y minus 1 is 7. So this thing is beta function of 2 plus 1, 7 plus 1. So this is beta function of 3, 8. And what is beta function of 3, 8? Beta function of 3, 8 is gamma function of 3 times gamma function of 8 all over gamma function of 3 plus 8 minus 1 or gamma function of 10, which looks, okay, a little bit spooky, but it turns out if I have a whole bunch of, this will happen a lot in a combinatorics class, if I have a whole bunch of factorials upstairs and downstairs, they'll always cancel. So it's actually pretty crazy when you do a couple of these in StatMech and you realize like, how am I always getting integers when I'm dividing these like really spooky looking ratios, which has to do something with number theory. But anyway, I got gamma 3, so that's 2 factorial, right? So the argument of the gamma function minus 1 factorial, and then there's 7 factorial, and then there's 10 factorial. Okay, so the 10 factorial has 10 times 9 times 8 times 7 times ... But then the 7 factorial has 7 times 6 times ... So in fact, all that's going to go away. So 7 on down is going to cancel from above. And so this turns out to be much nicer than it may first appear. So 2 factorial is just 2 times 1. So that's 2 factorial upstairs, or 2, and then 10 times 8 times 9 downstairs. 10 times 9 times 8, so like I said. And so that's 1 over 360. So congratulations, maybe use some paper, but you calculated the integral from 0 to 1 minus x all to the power of 7 in your head, essentially. So which is like kind of a dumb parlor trick until you realize that these show up a lot. So in stats, especially, the beta function is really important in Bayesian statistics, which is, at least culturally in the stats world, really important right now, because it lets you implicitly put your thumb on the scale for the answer that you want at the beginning, so you can be hired by a pharmaceutical company. Any questions about that? Okay, let's do another one, but with trig. So same thing, try to do this without Mathematica or Wolfram Alpha or anything. And this one should also be doable. Okay, sine to the 9th power phi times cosine phi d phi. And then we'll talk about the, the ways it's making these like actually tricky. So you guys a couple minutes for that one too. Is anybody happy with their answer? So this one should be a nicer number, I think. What'd you get?
I got 1/10.
Yep. So same story. You identify this as the right form, and I'll give it away is that the thing that's making this look easy is that we're just putting integer powers. You're gonna realize that these are fractional powers, and then somewhat absurdly, remember gamma and beta can be defined on the entire complex plane. So you could have these powers be complex numbers too eventually, which is kind of neat. So sine has power 9, and then cosine has power 1 implicitly. So an attempt at a trick which failed. So then I know that the beta function, this is maybe worth kind of scribbling down in a sidebar. So 2x minus 1 is equal to 9. So x is equal to 5. And then 2y minus 1, the power of the cosine is equal to 1. So y is equal to 1. So this is beta function of the two values 5, 1. Except I'm missing one little thing. So they've got that prefactor of 2. So technically what this is 1/2 of the beta function 5, 1. Right? So the sneaky little prefactor of 2 is missing. So I got to put that in there. So this is 1/2 beta 5, 1. And then, since they're integers, evaluating it through gamma functions seems the easiest. So this is gamma 5. Yuck, gamma 5. I tried to write. Gamma 0, or gamma 1, which is 0 factorial. And then gamma 5 plus 1 minus 1 is 5 factorial, or gamma 6. So that's 1/2 times 4 factorial times 0 factorial. Five factorial. And then same trick, the 0 factorial is 1, but then the 4 factorial and the 5 factorial, everything cancels aside from the 5. So we got 1/2 times 1/5 is 1/10. Okay, so those are the vanilla ways of using those two forms. You just identify and then you can calculate them if you need to, just to show off by hand with gamma functions. Realize this is also true if we had something that looked like this. So we could also have fractional powers. So this is totally fine. So the one thing we haven't talked about, and I'll just make a comment about, are the limits. Like, what can you do if somebody gives you goofy limits? So this is also okay. You would just have to put in those and you would get the beta function, or 1/2 of the beta function of like 9/4 and 4/7, which is gross, but it exists. So you probably have to use something, numerical algebra solver like Wolfram Alpha to actually solve that. But this is still a beta function of 2 arguments. Okay, the one thing we haven't talked about is, can you mess with the limits of these? I'll just say that a couple of things exist as a note. So you know that, if you ever do see an integral of this type, you know what it's called and can look it up. There are what are called incomplete gamma and beta functions. And because those are the ones I know offhand, I'll just write down kind of the mnemonic for what the incomplete gamma functions are. So there's an upper and a lower incomplete gamma function, where the gamma function itself, I integrate this right? So if I split that up, and we'll just, oh, I don't know, pick X, so kind of uncreative. Oops. Instead of doing the entire interval, if I integrate not from 0 to infinity, but from 0 to some point, this is what's called the lower incomplete gamma. Typically denoted with a lowercase gamma, and it's got two parameters. So you need to specify two things. You need to specify both n and x. So this would be xn, and this would be the upper incomplete gamma function. Capital G gamma x and likewise for the beta functions. So this isn't going from 0 to infinity. So just those are out there. But you know, at this point, you have the tools to look them up and understand some of their properties. So any questions about any of that? And then we'll do physics problems. So seems like it's been a while. Okay, tell me everything you know about the simple pendulum.
It's a simple harmonic motion. Can be solved with sines and cosines or complex exponentials.
Yes. But along the way, you had to do something shady, right?
Yeah. Substitute theta for sine theta in the equation of motion.
Yeah, and theta and sine theta to me don't really look alike. So you can actually solve the simple pendulum outside of the small angle approximation, and you'll get something that you now know how to at least plug in. But let me really quickly go over the physics. I guess you guys had a refresher on this in classical mechanics if you're talking about complex valued solutions, which is great. Okay, so like everything, I draw a free body diagram. I have tension, which always points up the rope, and then I have weight, which points down the rope. I realized that maybe the best thing to do is to use angular coordinates like theta. And I also, because we're outside of 1210, I know that really what I should be doing is talking about sum of all torques equals I alpha. Be around this pivot where this thing is attached to the roof, which means the tension has no torque. So the torque of tension, which I just like saying, is equal to 0, but the weight has some torque. Right? So that is 180 degrees. And then the thing itself is a point mass. So I would look up the moment of inertia of a point mass, which is just mr squared or ml squared. And now I gotta just figure out the torque of the weight. So the torque of the weight is mg, the force, sine of the angle in between. And that's going to be like related to this angle theta. And it turns out to be that angle theta. And then my definition of the right-hand rule, or realizing that this torque is a restoring force, I got a minus sign. So the bigger the theta is, the more it's going to want to torque in the clockwise direction. So one way or another, I really need a minus sign there. And then the moment of inertia of a point mass is mr squared, which in this case, that's the length, so L squared. And then the angular acceleration is theta double dot. So that's kind of the torquey way of doing that, but you've seen this before. So this is the full equation of motion. And what you're used to doing is, of course, saying that, Taylor approximation says that sine theta is just about equal to theta, provided I stay, to within 15 degrees. And I'll just point out that there's like, you shouldn't like that argument. You shouldn't like as long as you stay within some, whatever specified range, you'll be fine. So let's say that I was trying to navigate a boat across the Pacific Ocean and I was only off on my navigation by 1 degree. Like if you're walking to the bathroom and your navigation is off by 1 degree and the bathroom is 10 meters away, it's not a problem. But, there's this missing thing when people talk about approximations. Like if you're off by 1 degree and you're trying to land on an asteroid that's, 3 astronomical units away from Earth, that's a big deal. But anyway, slight digression. So we're not going to do this. So we're not going to use the small angle approximation anymore because we can actually solve this. So what's still true is these masses can go away though. So let me just rewrite this. I think I should have another L. Yeah, so there's a torque on, whoops, went too fast. There's an MGL here. This is a torque too. So this is mg acting at L sine theta. So I missed an L here. Go back and correct my mistake. Okay, so our full equation of motion is this: minus g over L sine theta equals theta double dot. There's a trick. So there's a trick, which will be to multiply by an integrating factor. And there's, sort of semi-art where choosing or finding integrating factors is just mostly pattern recognition. So in this case, the pattern recognition is going to let me express theta double dot as the derivative of something else. So it's going to be theta dot squared. And at some point somebody realized that, and that just got added to the set of tricks. So I'm going to multiply everything by theta dot. Well, actually, let me just make everything a little bit cleaner and let me multiply everything by 2 times theta dot. So 2 times theta dot, the whole thing, minus g over L sine theta, and then 2 theta dot, theta double dot. And the point of that is now this right-hand side term can be expressed as a total time derivative. So what that is now is d by dt of theta dot squared. And what that also lets me do on the left-hand side is not everything, but just theta. And honestly, this is the real point of the integrating factor, is that remember theta is a function of time. So I can't just say that like d by d sine theta. So d by dt, let's just do it, cosine of theta is not equal to minus sine theta because sine theta is a function of time. I also have a theta dot. And so basically I'm putting that in manually. This lets me express the right-hand side as d by dt of theta dot squared, but also, most importantly, it lets me represent the left-hand side by d by dt of cosine of theta. So that's minus sine theta, theta dot. Okay, so with that, the 2 is a little bit goofy on one side or the other. There's no way around that. I have this. Remembering that theta, again, is a function of time. Okay, So this is nicer, and that was a little bit of an active inspiration, so the choosing of an integrating factor. So what can I do here? Well, I have the fact a time derivative, total time derivative on the left and the right-hand side. So I can just integrate both sides by time, and I can get rid of that. And all of a sudden, my differential equation will become, excuse me, my equation of motion will look much, much nicer. So let me actually clear everything. So any questions about any of that so far? It's a little bit of inspiration, but whoever did this the first time, they knew where they were going. So they had a form of an equation that they were like, hunting for. And surprise, surprise, it's going to be a beta function. Okay, so we have 2g over L d by dt cosine of theta, which is a function of time, and then d by dt theta dot, which is also a function of time squared. So I'll just integrate by time. And physicists can do this. Mathematicians get enraged when you pull stunts like this. So fundamental theorem of calculus, integrals, undue derivatives, we're done. So now we have up to an integration constant, this. So we have 2gl cosine of theta. Again, it's a function of time. I'm going to stop writing it like that. Plus big ol' C integration constant plus theta dot squared. Or sorry, equals theta dot squared. So this is nicer. Okay, this is where things get a little bit probably abnormal from the usual treatment. Is you're used to evaluating integration constants after you're done. You can evaluate integration constants the second they show up. So I'm going to evaluate this integration constant and say, I can go back to the equations of motion, and essentially what this is saying is, what's the initial velocity squared, okay? Or I can rephrase it in terms of something with the same units. Or alternatively, if you're a mathematician, you can just say, like, I can rewrite this in such a way that it makes my life easier. But one way or another, you can write, this is a constant, right? So theta naught is a constant. It turns out theta naught is theta naught. So that's what you would be doing if you evaluated the integration constant right here. Again, the mathematician kind of agnostic way of saying it is like, look, I know what unit C has, and I can write it however I want. I can just write it this way to be convenient. But one way or another, we'll call the integration constant this. So then I have 2g over L cosine theta naught. That does actually turn out to be theta naught squared. And then I can just square root both sides and let myself undo the notation, and this is what theta dot is. So theta dot is d theta dt. And probably shouldn't like mix the radical and fractional power notation, but whatever. Okay, have you guys done finding equations of motion or implicit equations of motion through, we end up with this like nasty thing like u minus 1/2 mv squared. And then you unpack v into dx dt or dr dt, and then algebraically solve this. So actually, I think this is the usual way of doing it, to just straight up energy. And you end up with this thing like energy minus u of x.
We've been using the Laplacian a lot.
Okay.
we've been introduced to the Hamiltonian, but we haven't like used it a lot.
Okay, so have you seen, yeah, you'll see this. So probably when you guys do orbits, you'll see a treatment like this, where you literally write down the algebraic equation for the energy, and then you split V into dx dt and just solve it algebraically, and you get something that looks like really goofy. So you get a dx over there, and then you get a 1 over dt there, and then you flip everything. That's essentially what we're doing. So right now it might just look like hammering away at the math, but essentially it's this. Okay. So again, a thing that physicists totally fine with doing, mathematicians less so much. I am going to write this in the following way. Actually, write it in more of a mathy way. So dt root L over 2g, plus or minus, because we will throw away signs when we unsquare root this, d theta cos theta naught. And then this is the interesting part. So I can now ask, how long does it take to get from point A to point B? So I can integrate from 0 to 1 full period, and then I would integrate from 0 to theta naught, right? So this would be essentially technically 1/4 period. So I start at some theta naught, and then I end at 0, right? So that would be 1/4 period, that would be half period if I go out there, and then all the way back is a full period. So technically that would be, should write it what it is, write it as what it is. Okay, this is how you would find, for some arbitrary non-small angle approximation, this is how you would find the period, and it's going to turn out to be something that's less than the small angle approximation period, which is 2 pi times root L over G, because the restoring force gets weaker as you get higher and higher. So we'll do one specific example of this. So let's see how this would work for the worst of all possible scenarios. So right now we actually have an incomplete beta function, which we're not going to talk about, but you guys know how to look up if you want to do. Let me start here. So this is like the worst thing I could do, you know, if I actually had a string and not an inflexible rod. This is the worst thing I could do to test the small angle approximation. Like, I am at 90 degrees. So theta naught in this case is pi over 2. So how would that work out? Well, that would be a 1/4 period. And there's no point in even writing that anymore. It's like kind of a trivial integral. So we'll just say t over 4. So t over 4, root L over 2g, integral from 0 to pi over 2. Happy about that. D theta. And then what's cosine of pi over 2? So things are looking pretty nice. Cosine of little bar at the bottom of Zoom is getting in my way. Cosine of pi over 2, or written another way, t over 4 is equal to root L over 2g, integral from 0 to pi over 2. Cosine minus 1/2 theta d theta. Okay. Any ideas about how to solve this? Yes, because that's what we've been talking about all day. Write down the form of the beta function it would take. Clearly, this is the trig form because we have an integral from 0 to pi over 2. And this will involve two things. One is clearing away all the physics constants, which a lot of times gets people. And secondly, wait a minute, I don't even see a sign. So what does that mean about sign? So give you guys a couple of minutes to do that, and then we'll actually do this by hand too, to remind you of a formula. I think the Euler's reflection formula will show up in this. Okay, I can sort of intuit from body language, we're probably ready to go over this. Obviously, we're looking for a beta function. What's keeping this from looking like a real beta function?
There's no sign.
There's no sign. So I got to put in a sign to the 0 power, right? Because sign to the 0 power is equal to 1. So then that lets me formally identify the alpha and the beta. So remember, our rule is that the real part of the powers cannot be negative. So 0 is totally fine. And the little nitpick is that this should also have a 2 in front of it. So I got to put a 1/2 there. Okay, so this is now in the form of a beta function, everything there. And this is, if I look at, minus 1/2 is equal to 2 alpha minus 1, and 0 is equal to 2, call it beta minus 1. So then alpha is equal to 1/4, and then beta is equal to 1/2. So that sign to the 0 power corresponds to the family of beta functions with argument 1/2. Then this whole thing becomes beta 1/4, 1/2, or 1/2, 1/4, doesn't matter because it's symmetric. Okay. So just to rewrite that a little bit cleaner, this is equal to quarter period is 1/2 root L over 2G, beta function quarter half, or half quarter. Right. So they lied to you and they said that, at least until you get into incomplete beta functions, you can definitely solve the 90-degree angle initial condition. Okay, and I'll just do you guys take a couple of minutes to at least bash your head into this, to turn it into gamma functions and see what you could do. Yeah, at some point you end up with a quarter, so you have to, use Wolfram Alpha or Mathematica. But yeah, try it, see what happens. So this is gamma 1/4, gamma 1/2, gamma 1/2 plus 1/4 minus 1. So that's, or 1/2 plus 1/4, or 3/4 downstairs. Okay. I don't think this actually makes your life easier, but neither does taking a math methods and physics class. So maybe we'll just use this as a, I don't know, reminder of this thing existing. So you could, because I see 3/4 and a 1/4. Maybe there's some help from using Euler's reflection formula. Honestly, I just want to remind you guys this thing exists. Which says that gamma of z times gamma of 1 minus z. And I have a 1/4 and 3/4 there, so maybe this is useful. Sine pi z. With the obvious restrictions that z can't be integer, because then this blows up. But that's fine because the gamma function blows up. So that would mean that gamma of 1/4 times gamma of 3/4. So it doesn't help as much as you would think, because one's upstairs, one's downstairs, and we do still have the gamma 1/2, but we evaluated gamma 1/2. Gamma 1/2 is pi over root 2. So we have this, and it's kind of alchemy because I can actually determine what sine of pi times 1/4 is. So that's √2/2. So 2 pi over √2. And as far as this will let us go is I could get rid of one or the other of these. So for instance, I could just say that like gamma of, gamma 3/4, I think would be the easiest thing to get rid of, is equal to, well, so it shows up downstairs. So really what we want is 1 over gamma 3/4 is equal to gamma 1/4 times √2/2 pi. And so that at least like simplifies this. Like maybe you only get one lifeline to Wolfram alpha. I don't know how this would show up in real life. But we do know that gamma 1/2 is root pi. So we worked for that. And then now we have this. So, okay, maybe no point in doing this because you're going to have to reach into some computer algebra solver to get gamma 1/4 anyway, but whatever. So and then finally I gotta go in and look up gamma 1/4. Okay, so putting everything together is, it turns out, quarter period L over 2g gamma function squared of 1/4, 1 over √2 pi. Okay, well, let's compare this to what an actual quarter period should be if I were to just drop in the small angle approximation. So this is the small angle version. So the whole period is √2 pi, or 2 pi root L over G. So this would be pi over 2 root L over G. So that would be the quarter period. So T0 over 4. And clearly these are different, right? So, and if you numerically evaluate this, what you would get is T, the full period, is about 1.18 T0. So you're off by about 20%, which is significant if you were to try to use this. I mean, certainly for like a grandfather clock, if your pendulum arm is 20% off for a single swing, you're going to end up not being able to keep very good time. Okay, so if you wanted to not do 90 degrees, you would have to look up some properties of the incomplete beta functions and then put them into Mathematica, and it evaluates it numerically, but they exist. Okay. So any questions about any of that?